thanks for the invitation to come and speak here. It's a great pleasure to be here in this beautiful place. So this talk is going to be about 3D Gaussian splatting, and the idea is to explain a little bit how it all happened over the years, and to show that it's the result of many years of research rather than just something that came out of nowhere. So first, a disclaimer. I'm a computer graphics researcher, but I have dabbled in VR a little bit. So you can see this is a cave, right? One of those old devices that we used to use. We worked on manipulating using finger gestures, working around in the cave, and more recently on head-mounted displays. But despite that, my main research has always been computer graphics. And at the high level, our goal is to generate realistic 3D environments, allowing real-time navigation in 3D. So this is an example of realistic renderings that we can achieve. So how does this work? And most of you are familiar with this. We generally have a virtual scene that will be defined by artists, and we have a virtual camera and create an image. And in a bit more detail, we have what we call the physically based rendering pipeline, where artist starts by defining a geometry, and this is usually a painful, long task. Then they'll define the materials, saying, okay, I want this to be wood, I want this to be marble, and so on. And once you've done that, you need to define the cameras and the lights. In this case, the light is coming from the door on the open door, half-open door. And then you need to do an accurate light transport simulation, which these days is usually done using path tracing, which is illustrated with this little animation here. And of course, the big question is, and then after that happens, we can have like good quality, realistic looking environments. The big question is, how can you easily create these 3D scenes? And this has been one of the questions I've been looking at over the years. And of course, it is very relevant for virtual reality. In essence, in virtual reality, we need to create these assets, making it easy, making it fast to display. So in VR has the additional constraint of requiring 2 times 60 FPS at least, maybe even more these days. And the third aspect is to allow easy modification of these assets. So, as I said, this is my high-level goal, but my main motivation over the years has been to make it easy to create content for graphics and to allow real-time and immediate rendering, avoiding global illumination, so the accurate light transport step that is very expensive and very computationally expensive. So today, I'm going to be talking about one specific solution to these high-level goals, which are capturing a 3D scene from photos or video and allowing what we call free viewpoint navigation, which is a little bit of a misnomer because it's free within a limited space. And these days, this is typically called novel view synthesis. So this brings us to the world of computer vision. And computer vision typically starts with a real scene. They have real cameras because somebody takes pictures or video. And then as an output, you get camera poses, so the position and the orientation of the cameras, which are computed using computer vision algorithms, and approximate geometry. So we can put all of this together and say, well, okay, I have a real scene, I take the real cameras, and if I have perfect computer vision, then I get an ideal virtual scene, and then I can just place a virtual camera wherever I want and look around in the environment, problem solved. The problem is that it's not the case that you can do this. So computer vision gives you very approximate geometry and typically no or very little information on materials. So a long time ago, the first idea people had, and I'll explain a little bit how this happened, was to develop a technique called image-based rendering, where you started with this approximate geometry, and you had your real input cameras, so the photographs that you took. And if you wanted to create a view from a novel camera somewhere else, you would take pixels from the images, use what we call the proxy, the geometric proxy, to be able to reproject into the novel view, and then you had a blending step where you would blend images together to get the result. And this worked pretty well. And this brings me to the part of the talk which is a little bit of ancient history. The very first work in this domain was done at Berkeley by Paul de Bebec, and basically at the time, everything was manual reconstruction. So one needed to take these pictures and then click 6 points in each picture to make the correspondences to get the calibration. But then, and this was 1997, right? He managed to get these little models, and then by projecting the photographs on the models, he could create this very realistic, at the time at least, environment. So around this time, we were also involved in this domain, and I've given this talk a number of times already, but I did actually revisit it a little bit to put it into a context of VR, and it turns out there is a context in VR, because a lot of this work that developed over the years was motivated by virtual reality applications, and at least in the early years, it was funded by projects that had VR as a goal. So this was one of the first projects that we worked on, and the virtual reality equipment that we had at the time was a workbench, and there was also a cave at the foundation of the Hellenic world at the time. And here it was more about image-based modeling, so using the techniques that Paul had developed, and then just texturing the objects and using them in a cave in the various experiments that we did. And the second application was architecture. And here we developed a very first solution for image-based rendering, and you can just see it, it's very subtle, that the windows will change when we switch from one image to the other, which is projected onto the object. And the second application that we did, where we actually used the workbench, this was work that we did with architects, and it was designing the Place Garibaldi, which at the time, and it was an audio-visual application, so it was sound and video, and we had the architects actually use the workbench and make decisions between the different choices. And it was funny because when they looked at this virtual environment, they said, oh, it's going to be really hot if we remove the trees. And thankfully they didn't, so we kept the trees in Place Garibaldi after the development of the tramway project at the time. We also developed a solution with volumetric image-based rendering. And the idea here was to capture much more complex objects, such as trees, where clicking wouldn't really be a solution. And at the time, we had to put a sheet behind the tree because alpha matting didn't work. And we created a volume representation for the tree and projected the textures onto the volume. And this allowed us to create pretty realistic looking trees using the very beginning of image-based rendering techniques. And this volumetric approach we'll see actually is a precursor of many of the other things that we developed. So image-based rendering was one of the aspects at the time. So this was the late 1990s, early 2000s. And the second element, which is very important, and which is critical in the development of the work that we did afterwards, is point-based rendering. So point-based rendering was developed initially in the context of scanning projects, where people would scan objects and just have point observations. And the work by Simon Rizkiewicz and Marc Levoy was a very important step, which allowed the display of what was then very large meshes. And the Hans-Peter Pfister, Matthias Zwicker, and Mark Pauli were the three point brothers, as we called them then at ETH Zurich, who developed the techniques which were what we built on 23 years later, and which were critical to the work that we did. So we worked in this space as well, and we used it to develop what at the time were very complex environments. It, of course, looks funny now, but that was the case at the time. And these were the days of the first NVIDIA GPUs. That's when the people left Silicon Graphics and they founded NVIDIA. And this was, again, it was a turning point. Because suddenly, like before, you had to spend 30K to get a machine which could do computer graphics, and suddenly with 600 euros, you could get a machine that did pretty decent graphics. And that got us on this path of understanding how it works. Another example, and this is a kind of a funny story, because I had actually forgotten about this paper. But at the time, we combined the two. So we had point-based rendering, and Pierre, who had developed this calibrated camera system, and we reprojected it, and we could create a point-based reconstruction of the 3D scene. And this was in 2001, right? Obviously, it was a very simple brute force approach, so a lot of the technical elements were missing, but the ideas, the initial ideas, were already there. So there was kind of a fast forward to 2007, 2009, where the big change that happened is, as I said, initially, up to this point, all the steps were manual. So you had to click on the images, you had to click to create the polygons, and so on. And then structure from motion happened. This was, many people contributed. Noah Snavely's paper was the one that influenced graphics the most. And multi-view stereo, which allowed automatic camera calibration, so you no longer had to click to get the cameras, and you would actually get some geometry immediately. And just a note here, because geometry is going to be mentioned quite a bit, meshes are what are the primitive that's most used in computer graphics even today to represent the shape of objects. And it's important to realize that the most critical thing is that they provide normals to the surface, and they're represented by triangles. And that's something that dominated our research for a while, and it was, again, as we'll see later, it was a critical point where we had to move away from meshes. Anyway, to go back to SFM, this is just a simple illustration. Here we've taken 10 photographs of a scene, and this shows what structure from motion does. It allows you to position the cameras on orientation in space and creates a pretty decent textured mesh. But you'll notice that some objects are missing geometry, and other objects, there's too much. And this was a problem of the multi-view stereo techniques that do have another advantage, is that just the camera calibration creates a sparse point cloud, which we call the SFM points, which we'll be using later. So it was a major breakthrough, right? Suddenly, when I saw this, I said, wow, this is great. We can actually create content easily. And we worked quite a bit on using these techniques. But there was this problem of too much or missing geometry that we'll see was what we needed to deal with. So how did we decide to deal with this? Well, initially we just developed some simple techniques where here we project the four closest image to the new view, and we apply as rigid as possible transformations, which allows the geometry and the shape of the scenes which are reprojected to have a correct shape. And this was an interesting result, and we were very proud of the fact that we could move the camera quite far away from the input views. And the quality was actually pretty impressive. So the critical thing here was that we were using information in each of the input views, so that the information in the image compensates for the inaccuracy in the geometry. And that allows us to get better quality even though the geometric reconstruction isn't good. But it has the disadvantage that you need to keep these images around all the time, and that is a bit of a problem. So we worked on this, and we were involved again. All this was funded by European projects, and it was an interesting little experiment that we developed together with the Memory Center at the University Hospital in Nice. And again, this was in our cave at the time, although we were using just one screen, where elderly adults were presented with this image-based rendering of the Place Masséna, and they would manipulate it using a Schindler interface, and we demonstrated that it actually did help in some of the memory tasks that they were involved in. So these were kind of the dark ages of point-based rendering. Point-based rendering was peaked in the mid-2000s. There was a specialized Eurographics workshop and so on. But after this, interest sort of petered out, and mesh-based graphics dominated. And the reasons were that connectivity of the meshes is very important. You actually have triangles that are connected, so you don't need to deal with holes, which you do when you're doing point-based rendering. And there was high-quality texturing and materials. And it just kind of fell out of fashion. And around 2018, neural networks had started to appear and prove their utility. And in particular, for one task that we were interested in, which was blending, the blending step, blending can be seen as a filter. neural networks by that time had proven that they were the best way to do filtering. And we said, okay, well, maybe we can learn how to blend the images from data. And we combined this with a technique where we first improved the quality of each image. So this was a mesh generated by each image. And then we would combine the input images and compute the blending weights by, for a neural network would learn the blending weights. And this allowed us to get very good quality image-based rendering at the time. And to give you an idea, this was a comparison between a baseline method, and we can see that we're compensating for all the missing geometry and all the blending artifacts that happen using this combined technique. So deep blending solved the very hard blending problem for image-based rendering. And for us, this was an eye-opener moment, right? Suddenly we realized that this deep learning stuff is really important. And it can really solve problems that we were unable to solve before. And it allowed us to keep an eye on what was going on without completely deviating from the paths that we had chosen. We developed several solutions. Some of them were pretty complicated, but they did allow very good quality free view synthesis. And other people developed the techniques at the same time as well, like the guys in Munich, where they used neural networks to actually generate the image by encoding the information in different ways. And again, VR played a role in all of this research. We had a more recent project where we developed a solution which was used on a headset. So this is a visualization from the interactive experience that ran on a Vive. And it was interesting because there were major technological challenges. We dealt with thousands of images, and that helped us in our thinking. And it was very challenging to integrate image-based rendering into Unity. So we wanted to integrate deep blending, and at the time we were unable to, and we just stuck to a very basic solution. So what happened at this time, so this is 2019, 2020, image-based rendering got replaced by what became known as neural rendering. And the difference between image-based rendering and neural rendering is that you get rid of the geometry as a proxy, and instead you train a neural network that will contain the representation of the scene based on the information from the input cameras. And then to render, you just do inference, so you just query the network and it gives you the image. So there are various critical components that are necessary for this to happen. First, you need to get differentiable rendering. The way that neural networks work is they have a training step or optimization, and there's an objective function, a loss, which is typically the difference between a rendered image and a photograph. And for it to work, to be able to do this, to create this optimization, you need to have a differentiable rendering function that will give the gradients to the optimization so that it can work. And the big problem is that most rendering algorithms are not differentiable, at least in their original form. And one of the reasons, there are many, but one of the reasons is that meshes have hard edges that give abrupt discontinuities, which doesn't help in the optimization. And what happened at this point is in 2019, 2020, was the introduction of Neural Radiance Fields by the guys at Berkeley, helped with by the guys at Google. And this was a major revolution, right? NeRFs really changed the way that we looked at novel view synthesis completely. So how does it work? The idea is that you take your input images and you do a volumetric, you consider that it's a volumetric representation. So the neural network is going to output color, RGB, and density, which is a volumetric quantity, which is a proxy for the geometry. And as input, it takes a spatial location, which is typically going to be a sample along the rays, which you march, and a view direction. And you train the neural network to learn the representation. So this sort of vaguely reminds us of the volumetric representation that we had developed. And the key components of this ray marching and the fact that you have this neural network that you have to evaluate along the ray, which is very expensive. So the results were amazing, right? We had never seen this level of quality from novel view synthesis before. And basically, at the time, my question was, why would you want to ray march a volume when in the end we have surfaces, and are neural networks really worth it? And these were two of the things that motivated the research that we did after that. So moving to 3D Gaussian splatting was a relatively long process, and it was funded by my first ERC, so ERC FUNGRAPH, where the goal was to develop techniques to deal with uncertainty in data. So as I said, this incorrect geometry that you get from the capture process. And we developed solutions basically exploiting deep learning. And we worked on geosynthesis, relighting, and material estimation. I'm going to be presenting today mostly the results on geosynthesis. So the goals and motivations, the goal was to move from what was image-based rendering to an optimized representation, which has differentiable rendering for optimization, but we wanted to get rid of multi-view stereo and meshes because they're inaccurate and hard to optimize. We wanted to have fast rendering, so ray marching was probably not the correct option, and we wanted to exploit the power of these massively parallel GPUs, which over the years, since we were early adopters, we really knew how to use as graphics people. G is graphics in the GPU, even these days it mostly doesn't do graphics. And it was a long process with many non-obvious steps. So how do you replace volume ray marching? So at the time, my PhD student, George Kopanas, and Thomas Leimkuller, the postdoc, came up to me and said, how about points? And I said, are you serious? We did that 10 years ago. It doesn't work. Thankfully, I was sufficiently enlightened to say, but okay, I'll let you give it a try. And that was probably the best decision I ever made, right? So how does it work? As I said, this was work developed by the guys at ETH Zurich, and we have splats. So what are splats? Splats are these little things that live on the surface that have a normal, and we project them to the screen and we reconstruct using a Gaussian reconstruction kernel. And again, this is sort of reminiscent of the work we did on points a long time ago. So the idea, just as a visualization of these circles or splats, when they're flat, is that they exist on this surface and they have this little normal. So you need to have the mesh to be able to have a position and the normal. And their properties are that they become bigger as the camera approaches. So this doesn't completely solve, but it makes it easier to deal with holes. The other interesting property is that slanted normals appear as ellipses on the screen. So this allows us to model edges. And finally, each sample can be processed independently, which allows us to exploit massive GPU parallelism. That's all very well, but as I said, we need it to be differentiable. And again, the guys at ETH, well, other people, a different set of people at ETH, came up with a solution to this and showed that it is possible to have an end-to-end differentiable surface splatting approach. So we built on this solution, but we had to bring a few very significant changes to allow image-based optimization, because this approach was just for geometry that existed, and allow high-quality reconstruction removing geometry. So how are points blended in screen space? In the standard method of surface splatting, it's just a weighted average of the colors. And here the idea is that these methods, you have to remember, were developed in the case where the geometry is known. So it's okay to do this because the splats are going to be very close to the surface. Our context is slightly different. We have points in the beginning that are going to be kind of all over the place, and we don't know where the surface is, and the optimization has to find the surface. So instead, we just used a typical front-to-back alpha blending technique that allowed us to take everything into account. So this is good, but it's not enough, because we need to make points disappear. And to make points disappear, we need to add this additional factor, which we called opacity, which is probably not a good idea as it turns out, but which allows you to go to 0, which means that the point will disappear because it will become invisible. And it's interesting to see that this equation and the model that was used in NeRF, which is the volumetric equation, are essentially the same image formation model. That being said, the quantities are different, and we have a recent paper which explains exactly the differences between the two. So this was a thesis of George Kopanas, and it had several elements, that, with the Gaussian splatting being his third major contribution. And the first step was to develop a point-based neural rendering approach with purview optimization. And as before, the goal is to take casually captured images and allow high-quality rendering. So how does this work? Again, as I said, George and Thomas convinced me that points were a good idea. So you take the input views, so again, you have to deal with these input views, and you take the pixels that you can lift to 3D, and we do this because we use the multi-view stereo as a first step, and then you can reproject them to the novel view. Once you do this, you get a set of buffers of rasterized point clouds from each one of these views, and you use a neural network to interpret these rasterized point clouds to create the final image. And then you can backpropagate the gradients of the image, because you compared this to one of the photographs, and this allows you to optimize the parameters, for example, move the points around so they get closer to the place where they need to be. The method had various elements. I won't insist on most of them. One of the aspects was rasterizing point clouds, and this is the major change that we had to make with to the work on differentiable surface splatting. We had to add the additional direction of the input view to 3D and then to the novel view, which adds an additional Jacobian in the computation. And the second aspect I'll talk about very briefly is this purview optimization. So here, I'll let it run a couple of times. Initially, you have a 6-channel feature vector, which extends the RGB color channel and allows the neural network to have more capacity to interpret things. So in the beginning, you get a gray image. We'll wait until this ends. And if you look here, there's not much texture, and as time goes by and the features are optimized, the texture becomes sharper and sharper. And we also optimize depth, normal, and uncertainty. And the results are pretty good, right? So, if we compare to, can I go back? Yes, I can go back. If we compare to deep blending at the time, we can see that we had much sharper vegetation and much better robustness to incorrect geometry. And even compared to NeRF, which was hard to do at the time because NeRF couldn't handle this kind of scenes, we had much sharper geometry. And the thing is that this method took something like a few minutes to generate one image, and we were at a few images per second. So this first step was important because it allowed us to correct some of the multi-view stereo mesh errors. We had rasterization for differentiable rendering, and the CNN that we used, the neural network to produce the image, produced sharp, high-quality results. But CNNs are prone to flickering in motion, and that was a bit of a problem. And unfortunately, we still needed the meshes as input so that we could get the positions in the normals. There is this flickering, and optimization was very slow. It was 18 to 20 hours, and even though rendering was much faster than anybody else, 5 frames per second is nowhere close to the speed that we need. The second project I won't talk much about. It was just treating the special case of shiny objects, but it has a few interesting components that were critical to what we did next. So we had a neural field, which was a multi-layer perceptron, which is a different architecture of neural network to move the reflections. But most importantly, the basic part of the scene, so the diffuse part of the scene, was represented as a primary point cloud, and we just rasterized again as we did before, and a neural network just generated the image by combining the two parts. So the critical thing was that we realized that we don't need the purview information anymore. So this project was a very important step, which allowed us to say, okay, let's just optimize all the points in 3D. So one day, George comes into my office and said, I'm going to try it, and the next day he said, it just worked. So that was a very important realization, so that allowed us to get rid of keeping the images around. And this had already been done by NeRF, but I mean, the ideas take a little bit of time to sort of, it was about the same time anyway. And the second aspect was the fact that the multi-layer perceptron doesn't have the problems of the CNN in terms of temporal flickering. And the results were very good. Again, compared to NeRF, which was the standard at the time, we had sharper reflections and a better overall result. So, as I said, point number one, we got rid of the purview information. The second important element, which was, again, a precursor of what we did for Gaussian splatting, was the need to densify. So we first test based on gradients, and we had rasterization for differentiable rendering and the MLP I talked about before. So again, the optimization is still slow, and we didn't really understand why, right? Why was it so slow? Why did it take so long? It was rasterization. It should be much faster. And we still needed the MVS meshes because we needed the normals. And this is an important point. We actually did experiment in this project with 3D Gaussians, but we didn't manage to make it work. And why was that? Because each cycle required 18 hours. So we tried it for a week. We had like, 5 or 6 tries, and then we gave up. And I'll come back to speed afterwards. So this brings me to 3D Gaussian splatting. Again, this was in the context of George's PhD. And an important newcomer was Bernard, Bernard Kerbel is an expert in GPU programming, and in particular, point-based rendering for GPUs, and that was a critical aspect for this project. So what were our goals? We wanted to remove multi-view stereo, get rid of the meshes, extend circles to be efficient and effective 3D Gaussians instead, remove all neural rendering components, and be fast, efficient, and accurate at the same time if possible. And as a preview of the results, this was the work that was presented by NVIDIA the year before ours, and we can see that we're getting slightly better quality at much faster speed. So how do you extend to these 2D circles to 3D Gaussians? As I said, circles are these little points, so there's a position, a normal, and we used the standard deviation for the Gaussian kernel reconstruction, opacity, and this appearance vector. And to go to 3D, it's pretty easy. You just need generalize the same concept. You have a position, then you have a covariance matrix that is the equivalent of standard deviation in 3D. We kept the opacity parameter, and instead of using a neural network, we just use spherical harmonics, which is standard graphics representation for directional radiance. So what is the benefit? Well, we can initialize just using the initial SFM points that I showed at the beginning. We don't need the normals, we don't need the multi-view stereo anymore, and SFM is just the camera calibration step. We start with isotropic Gaussians, so spheres, and then the advantage of having this anisotropic Gaussian representation is that we can get these things, these primitives, to fit all sorts of different shapes, such as vegetation. So this is an example of the SFM points that you get as input, and this is a visualization of the ellipsoids that are used to do the actual reconstruction, and this is the result of the blending that you get the high quality rendering at the end. So how do we render? Well, the first thing you need to do is you need to sort globally on depth, because you need to do this back to front blending step, and then you need to splat, so you take the 3D primitive that you splat into the screen, and then you blend using alpha compositing. So how did we go from 5 frames per second to 100+ frames per second, and most importantly, from 18 hours to 5 minutes for training or optimization? So this was Bernard's expertise, and when he came into the group and we started working, we said, okay, this is our CUDA code, what do you think? He didn't burst out laughing, but he almost did, right? He said, well, yeah, but I mean, how can you possibly do this? And he explained that there are a number of things that you need to do to make the cores on the GPU work well, and the first is you need to split the image into tiles so that the threads can work together better. And most importantly, we were doing per pixel sorting, which basically meant that all of the cores were waiting for each other, and it was essentially almost not parallel. And GPUs can do global sorting of millions of primitives in, I don't know, 5, 6 milliseconds. And those two things were the elements that changed things completely. During the optimization on the training phase, we optimize all the properties, opacity, position, etc. And then we used standard deep learning machinery, so PyTorch, the Adam optimizer, and so on. So even though technically speaking Gaussian splatting is not a learning method, it would not have been possibly if we hadn't used all of the infrastructure that is provided by deep learning. We use an L1 loss with the training views and a perceptual metric, and LPIPs and central metric. So you have the SFM points, you do your optimization, what happens? This is what you get. This looks okay, But as you can see, there are things that could be improved. So notably in this little zone, you see that the quality gets a lot better. And why can we not get better quality? There are not enough points. We don't have enough points and they're not in the right position. So we had to develop this densification approach, which we had initially experimented in the previous project, where basically if during the optimization the points have high gradients, so they're trying to move around a lot, that probably means that they're not in the right place. So those are the places where we add points, and we have two ways of doing that, splitting and cloning, depending on the size of the primitive. And this is an illustration of the time lapse of training that shows, this is about ×4, I think, speed up. You go from the case, in this case for these simple scenes, it's just the random initialization. So we evaluated on 3 different data sets. So that, it turns out that this was a critical decision, probably not with the correct motivation. My motivation was, oh, I don't like the Google scenes, I want to try the other ones. But it turns out that it's very, very important to develop your algorithm on different kinds of data. So these scenes each have completely different characteristics. The MIP-NeRF 360 are basically these circular captures around a scene. Tanks and temples are these video sequences kind of in the wild, and the deep blending scenes are what we had developed specifically for the previous method. So each one of these was captured in a different goal. And as a result, George optimized the parameters so that the method worked well on all scenes. And as a result, it's a very good compromise. And we can see this in the results in terms of image quality. We're about as good as MIP-NeRF 360 and even better in the perceptual metric. But there, where we see the big difference is that we're like way faster in terms of display time and training time. MIP-NeRF 360, it was 48 hours. Now the NVIDIA method trains quickly, but it plateaus. Because of the grid representation, you can keep on training, it won't get any better. But we were kind of annoyed with this. We said, yeah, I know, but I mean, why is this the case? So we said, okay, instead of going to the 30,000 iterations that we did, we'll try and find about the same speed as NVIDIA. And we saw that basically at that speed, we are about the same quality, but we're much faster in display time. But the key element is that if you keep on training just for another 30 minutes, you get the quality of 48 hours. And that's the big difference, as well as the fact that you can get, you're basically at the interactive speed that you need. Memory was a problem, but we solved that later. So if we compare, this is my favorite little sort of asterisk slide, you know, the little lab in France that can go do better than the giant American companies, and NVIDIA as well. And we can see that basically we're better and faster, and the quality our method allows us to capture details that the other methods, which were much more expensive, could not do. And I'm running a bit late, so I'm going to go a little bit faster here. So the method found the sweet spot between volumetric rendering, which we implemented using opacity and alpha blending, but we used it in the rasterization context, so we avoided the expensive gray marching step. We had excellent results in both speed and quality, greatly accelerating both the training and the rendering. No neural networks, which a lot of people have made a big deal out of this. I don't think it's such a critical point. I mean, these days, a very small MLP can probably be as fast as spherical harmonics. It wasn't a religious choice, it's just the first choice we made. It's perfectly fine to use small neural networks these days as well, and there's dedicated hardware which makes it very fast. The memory was still high, but we kind of solved that. So the uptake took us by surprise to a certain extent. When we published the paper, like when we submitted the paper, I said, this is it, it really works. But I could never imagine how popular it would become. So basically it's been implemented in all of the standard engines, and that very early along. Our code is open source, but with a dual license, so it's free for research and evaluation, but people have to pay if they want to use it commercially. And we've sold several licenses to e-commerce, high-end visual effects, 3D content creation, online social networks, telecommunications. And one company that was a very early adopter is Infinite Realities, that have a service, they have a capture setup which can create this kind of content. So this is a multi-camera version. So basically for each frame, they create a Gaussian splat and they play it together. But the realism is amazing, right? You can move around in the cameras and it just, it blows the mind. Another company that licensed from us is Vario, and they have developed a project called Teleport, which is a virtual reality setting. And you can see the quality of the captures that you can create, and you can move around and really be there. There are many other cases. Meta announced Hyperscape, which uses Gaussian splats. Adobe uses it for generative 3D. And a surprising one is the New York Times. It's R&D, but the idea is what they call spatial journalism, which allows you to create 3D experiences for the news. Scientifically, there's been hundreds of follow-up papers. It's hard to keep track. I get like an alert with 40 papers every morning on people who develop follow-ups. Basically, most of the problems have been solved, the memory and so on. I'll talk about that a little bit later. Generative models are interesting, especially diffusion models and video models. That's a subject for another talk. We developed a solution for memory reduction as well as many others, so it's 25 times less memory. These days, memory isn't a big deal. And a method for large scenes, which was presented last year at SIGGRAPH. The problem is that using the standard method, if you start having a scene with 22,000 images, it won't fit in a 48 gigabyte GPU. And if you have 40,000 images, it won't fit in the largest GPU available. Well, I guess now there's a 96 gigabyte one, but still it won't fit. So we use standard graphics techniques by a divide and conquer approach with a hierarchy within each one of the cells, which we consolidate. And then you can choose your level in the hierarchy depending on where you want to be. So here, for example, we've chosen the lowest level. We get 40 FPS, but high quality. While if we switch to a higher cut in the tree, the quality is lower, but we have 70 frames per second, so that it's better. And this is a visualization of the result we got by a capture that I did on a bike on about 5 kilometers an hour for 1 full hour in the city of Nice. And this is kind of a dream that I've always had. I've always wanted to be able to do this, and being actually getting to the point where it's possible is extremely satisfying. That being said, this method is quite complex, but better solutions are on the way. So, sort of to talk a little bit about the future, I was lucky enough to get a second ERC this year, and the story I sold in the proposal is that we want to develop a new 3D scene representation and companion rendering algorithms which can benefit from all of the advances of these generative deep learning models that you've all seen, Midjourney and so on for images, and Sora and all the other runway models for video. These models are all very good, but they have no notion of physics in the image formation and no notion of control in physically based principles. So the idea is to develop a representation that will allow us to benefit both from those and physically based rendering and the rendering algorithms that go together. And all of this, of course, is necessary for VR because it will allow you to have controllable assets rather than this just black box learning approach. So to give you an idea of the kind of thing we want to do, these are a couple of recent results. So this was a paper we presented last year, which uses a diffusion model that is one of these generative techniques that generates very, very realistic images. So training it is impossible for us, right? It requires 45 days on 100 GPUs at the cost of millions of dollars. But these models are available, or some of them are available, and what you can do is you can fine-tune them at a much lower cost, something like 3 or 4 days on a single GPU or 4 GPUs, on a specific data set, and it's called conditioning, so that you can fine-tune these models to do a specific task. The specific task we trained it to do is to do relighting of images. So there's this small data set, it's about 2,000 or 4,000 images, but what the guys did is that at MIT is they took a camera with a moving flash, a motorized flash, and they took 25 illumination conditions of the same scene. And they took, I don't know, a few hundred scenes like this. So what we did is that we applied this fine-tuning technique on Stable Diffusion that allows us to, with a method called ControlNet from Berkeley, that allows you to train a network to take a photograph as input and create these 25 lighting conditions that are where the direction of the lighting can be estimated. So once we have that, what do? We take the pictures as we do usually of a single scene, and then each one of the input photos, we create 25 versions of it in different lighting. And then we need to modify the training algorithm, so instead of having spherical harmonics, we have a small multi-layer perceptron that takes the view direction and the lighting direction as a condition and can produce, it trains a model. So now we have a Gaussian splat, which is not just a Gaussian splat, but it also understands lighting direction, which is shown here symbolically with the diffuse ball, which shows the direction of lighting. And what's fascinating in this result is the level of realism. It's very, very convincing. It looks realistic, but the problem is that there's only a vague notion of light direction, and there's no truly physically based control. And that's the goal of the future work, is to come up with a way we're actually controlling these things. A second example is in sort of a similar vein. It's older technology. It's using GANs and triplanes and NeRFs, actually. But the idea is similar. So we're able to, we have a physically based rendering model for the reflections of cars, but it is a generative model. We can change the kind of car that we have interactively using the generative adversarial network. And this is all very well, but even though it's powerful generative capacity, the geometry isn't super accurate. You'll see that the mirrors aren't great and so on. There's no error control, and there's only an approximate notion of materials, which is not enough. We want to be able to have a true computer graphics approach. So the challenges are multiple. First is that current representations are unsuitable. They're either good for rendering or physically based rendering, or good for optimization, but rarely both. Designing fast, accurate, and differentiable renders is a hard problem, and we're attacking it from different ways right now, on the physically based end and on the optimization end. And generative models are hard to control, and we're hoping that these good representations and renderers should help. The other problem with generative models is that they change every second week, so keeping up with the techniques is hard. But the approach we take is to try and identify what all the big companies are doing and go off on a slight tangent in something that doesn't directly interest them, but is still interesting enough. And that seems to work. So, to conclude, looking back, novel view synthesis is now usable for many applications, as I hopefully demonstrated. It took more than 20 years to get there. And it's kind of a satisfactory feeling to say that this is sort of solved. But is it really solved? Not completely. If we really want to be able to make this usable, we need to have solve the first problem, is that camera calibration is still slow and inaccurate, and the optimization is fast, but it's not fast enough. What ideally we would like is real time. You take your pictures, you have your 3D. It's not that far. Relighting, editing of content, all of these problems are things that need to be solved, and relighting, really solving relighting in the general case is a really hard problem. If we manage to solve that by the end of the project, I'll be happy. Extracting these physically based rendering representations is important, and making everything work together in the most convenient way is also critical, and there's a lot of, I think, user experience in that as well. All of this is, of course, indispensable for this to be really usable in VR applications. If we want to get to the point when you don't need to have artists do any content creation at all, but you can just create your environments, there's still a lot of work to be done, and all of these components are necessary. So looking back, what are the keys to success? It's hard to say, and I just arbitrarily chose some of them. The first one is be mindful to a rapidly changing field. So it's hard, right? Things change so fast, it's really hard to keep up to date. And you need to carefully balance avoiding adopting powerful new tools, because they are powerful and they can solve problems, and at the same time, avoid jumping on the trendy wagon. So when NeRF came out, everybody started doing NeRFs. And because I'm, probably, just it's just a bad part of my character, said, no, I don't want to do that. And it turned out that it was the right choice, right? Because we insisted that, oh, what we're doing has value, it's worth it, let's keep on doing it. But we were inspired by all the methodology that was around us. And you need to exploit your strengths. Our strengths were core graphics. And there's still a lot of things in core graphics, and all of the literature is 50 years of computer graphics literature that can still be very useful, and we want to exploit it. And third point is this balance between advance quickly, leave optimization until later, which is my standard advice to graduate students, and then you realize, well, maybe not. If you optimize now, that can help you advance faster. Again, it's a balancing act, but you need to be careful, because if you're, especially with these learning, if you start doing deep learning, if your turnaround cycle is 3 days, it's really hard to advance, and it's really frustrating for the students. The other points are acknowledge your errors as early as possible. We all make mistakes, and fixing them makes us stronger. And the example of my reaction to doing point-based rendering is an example, and there were many others, of course. ERC funding, I can't say, and there's no words are enough to say how great it is. Basically, for 5 years, you don't have to do grant proposals. You can instantly hire people. Bernard showed up, sent me an email saying, oh, I would like to do a postdoc. I said, right, start tomorrow. So that's the kind of thing that you can do with this funding, which is amazing. And a personal preference is small, flexible teams. I find that for research, in academic research at least, it's what works best and what we can do. And finally, and most importantly of all, you have to have fun. If you're not having fun and you're doing research, you just can't do good research. So thanks very much.